Welcome to Conventional Production Logging, Two-Phase Flow Fundamentals module. This section provides an introduction to the module and explains the importance of the topic. Why does one need to know how to identify fluid entries and calculate flow rates downhole? Production logging measurements provide the only way to know for sure from which formation which fluids are being produced and at what rates. Reliance on surface rates and commingled flow allocation based on permeability estimates can lead to attributing production to the wrong intervals, which may result in reservoir mismanagement. If one does not get this right, one may cone gas into oil intervals or smear oil into gas caps. This can result in the loss of millions of barrels of recoverable oil, which can lead to loss of tens to hundreds of millions of dollars of revenue. In this module, you will learn what flow regimes are and how they change with changing water versus hydrocarbon flow rates, basic fluid properties and how to use them to convert downhole flow rates to surface flow rates, how to identify fluid entries, determine the types of fluids entering the wellbore, and calculate water holdup using the following fluid holdup measurements: pressure depth derivative fluid density, differential pressure fluid density, capacitance, focused gamma fluid density, non-focused gamma count rate, and backscattered gamma gas holdup measurements. What slip velocity is in two-phase flow and how it relates the velocity of the less dense fluid to that of the denser fluid. How to calculate two-phase flow rates from a multiple pass spinner and fluid holdup logging survey, and some basic ideas on how to deal with non-bubble two-phase flow. Flow regimes describe how a less dense fluid moves relative to a more dense fluid as a function of their superficial velocities. Superficial velocity is the velocity a given fluid phase in two-phase flow would have if it alone occupied the borehole. There are four basic flow regimes in oil, water, and gas water flow in vertical wells: bubble, slug, churn, and mist or annular mist flow. At higher water superficial velocities, there are two more less common flow regimes: froth and dispersed bubble flow. As superficial gas or oil velocity increases for a given superficial water velocity, it occupies more of the total volume, and gas bubbles coalesce into slugs, which then deform into churns and eventually become the continuous phase with water suspended as mist bubbles. When hole deviation increases toward horizontal, two more flow regimes appear: stratified and wavy stratified. Gas, oil, and water densities are required to calculate water holdup from fluid density measurements. Gas density can be calculated from gas composition, temperature, and pressure using the non-ideal gas law. Gas, oil, and water formation volume factors are required to convert downhole flow rates into surface rates. The gas formation volume factor can be calculated from the non-ideal gas law. The oil formation volume factor is best determined from laboratory measurements, but can often be estimated from correlations, of which Standing's correlation is the most common one. The water formation volume factor is fairly close to unity, but can be measured in the laboratory or estimated from a simple equation. Water holdup can be calculated from the following fluid holdup measurements: pressure depth derivative fluid density, differential pressure fluid density, capacitance, focused gamma fluid density, non-focused gamma count rate, and backscattered gamma gas holdup measurements. Pressure and differential pressure fluid density measurements lose sensitivity as hole deviation increases and usually are not recommended for hole deviations above 60 degrees. They do average across the entire wellbore. Capacitance and focused gamma density measurements only measure what is within their sensing volume and are not accurate when both fluid phases are not well mixed. Capacitance measurements can be quite nonlinear and difficult to use, whereas focused gamma fluid density measurements are linear when the two phases are well mixed. Non-focused gamma count rate measurements are valid for any hole deviation, but they are sensitive to what is behind the casing as well as to the fluids in the casing. Backscattered gamma gas holdup measurements are valid for any hole deviation and are almost linear for casing sizes up to 9 inches in diameter. Two-phase flow rate calculations require a spinner measurement for an estimate of the average flow velocity and hence total flow rate. They also require a water holdup measurement and a slip velocity measurement to determine the amount of each phase present and its average velocity from which water and hydrocarbon rates can be calculated. Slip velocity models for bubble flow are well defined as a function of water holdup for oil-water flow and as a function of density difference for gas-water flow. Slip velocities for slug and churn flow are more difficult to determine, but some simple equations exist for vertical wells. Their behavior as well deviation increases becomes more complex, but slip velocity tends to increase as hole deviation increases.